11. Analysis of variance and covariance. Analysis of variance ANOVA. Analysis of variance, abbreviated as ANOVA, is an extremely useful technique concerning researches in the fields of economics, biology, education, psychology, sociology, business, industry, and in researches of several other disciplines. This technique is used when multiple sample cases are involved. As stated earlier, the significance of the difference between the means of two samples can be judged through either t-test or the t-test, but the difficulty arises when we happen to examine the significance of the difference amongst more than two sample means at the same time. The ANOVA technique enables us to perform this simultaneous test and as such is considered to be an important tool of analysis in the hands of a researcher. Using this technique, one can draw inferences about whether the samples have been drawn from populations having the same mean. The ANOVA technique is important in the context of all those situations where we want to compare more than two populations, such as in comparing the yield of crop from several varieties of seeds, the gasoline mileage of 4 automobiles, the smoking habits of 5 groups of university students, and so on. In such circumstances, one generally does not want to consider all possible combinations of two populations at a time, for that would require a great number of tests before we would be able to arrive at a decision. This would also consume lot of time and money, and even then certain relationships may be left unidentified, particularly the interaction effects. Therefore, one quite often utilizes the ANOVA technique and through it investigates the differences among the means of all the population simultaneously. What is ANOVA? Professor R.A. Fisher was the first man to use the term variance asterisk, and in fact, it was he who developed a very elaborate theory concerning ANOVA, explaining its usefulness in practical field. Later on, Professor Snedeker and many others contributed to the development of this technique. ANOVA is essentially a procedure for testing the difference among different groups of data for homogeneity. The essence of ANOVA is that the total amount of variation in a set of data is broken down into two types, that amount which can be attributed to chance and that amount which can be attributed to specified causes. One, there may be variation between samples and also within sample items. ANOVA consists in splitting the variance for analytical purposes. Hence, it is a method of analyzing the variance to which a response is subject into its various components corresponding to various sources of variation. Through this technique, one can explain whether various varieties of seeds or fertilizers or soils differ significantly so that a policy decision could be taken accordingly concerning a particular variety in the context of agriculture researches. Similarly, the differences in various types of feed prepared for a particular class of animal or various types of drugs manufactured for curing a specific disease may be studied and judged to be significant or not through the application of ANOVA technique. Likewise, a manager of a big concern can analyze the performance of various salesmen of his concern in order to know whether their performances differ significantly. Thus, through ANOVA technique one can, in general, investigate any number of factors which are hypothesized or said to influence the dependent variable. One may as well investigate the differences amongst various categories within each of these factors which may have a large number of possible values. If we take only one factor and investigate the differences amongst its various categories having numerous possible values, we are said to use one-way ANOVA, and in case we investigate two factors at the same time, then we use two-way ANOVA. In a two or more way ANOVA, the interaction, i.e., interrelation between two independent variables factors, if any, between two independent variables affecting a dependent variable can as well be studied for better decisions. The basic principle of ANOVA. The basic principle of ANOVA is to test for differences among the means of the populations by examining the amount of variation within each of these samples relative to the amount of variation between the samples. In terms of variation within the given population, it is assumed that the values of Xij differ from the mean of this population only because of random effect C.E. There are influences on Xij which are unexplainable, whereas in examining differences between populations, we assume that the difference between the mean of the JTH population and the grand mean is attributable to what is called a specific factor or what is technically described as treatment effect. Thus, while using ANOVA, we assume that each of the samples is drawn from a normal population and that each of these populations has the same variance. We also assume that all factors other than the one or more being tested are effectively controlled. This, in other words, means that we assume the absence of many factors that might affect our conclusions concerning the factors to be studied. In short, we have to make two estimates of population variance with one based on between samples variance and the other based on within samples variance. Then the said two estimates of population variance are compared with F-test, wherein we work out F estimate of population variance based on between samples variance, estimate of population variance based on within samples variance. I2. This value of F is to be compared to the F limit for given degrees of freedom. If the F value we work out is equal or exceeds asterisk the F limit value to be seen from F tables No. 4a and 4b given in appendix, we may say that there are significant differences between the sample means. ANOVA technique. One-way or single factor ANOVA. Under the one-way ANOVA, we consider only one factor and then observe that the reason for said factor to be important is that several possible types of samples can occur within that factor. We then determine if there are differences within that factor. The technique involves following steps. I. Obtain the mean of each sample I. Obtain when there are k samples. 2. Work out the mean of the sample means as follows. 3. Take the deviations of the sample means from the mean of the sample means and calculate the square of such deviations, which may be multiplied by the number of items in the corresponding sample, and then obtain their total. This is known as the sum of squares for variance between the samples, or SS between. Symbolically, this can be written SS between is equal to 4. Divide the result of the 3 step by the degrees of freedom between the samples to obtain variance or mean square MS between samples. Symbolically, this can be written MS between is equal to SS between K1, where K1 represents degrees of freedom DF between samples. We obtain the deviations of values of sample items for all the samples from corresponding means of the samples and calculate the squares of such deviations and then obtain their total. This total is known as the sum of squares for variance within samples, or SS within. Symbolically, this can be written SS within is equal to 6. Divide the result of V step by the degrees of freedom within samples to obtain the variance or mean square MS within samples. Symbolically, this can be written MS within is equal to SS within. NK, where NK represents degrees of freedom within samples. N is equal to total number of items in all the samples, i.e., N1 plus N2 plus NKK is equal to number of samples. 7. For a check, the sum of squares of deviations for total variance can also be worked out by adding the squares of deviations when the deviations for the individual items in all the samples have been taken from the mean of the sample means. Symbolically, this can be written: SS for total variance is equal to, this total should be equal to the total of the result of the 3 and V steps explained above, i.e., SS for total variance is equal to SS between plus SS within. The degrees of freedom for total variance will be equal to the number of items in all samples minus 1, i.e., N1. The degrees of freedom for between and within must add up to the degrees of freedom for total variance, i.e., N1 is equal to K1 plus Nk. This fact explains the additive property of the ANOVA technique. 8. Finally, F ratio may be worked out as under: F ratio is equal to MS between, MS within. This ratio is used to judge whether difference among several sample means is significant or is just a matter of sampling fluctuations. For this purpose, we look into the table asterisk, giving the values of F for given degrees of freedom at different levels of significance. If the worked out value of F, as stated above, is less than the table value of F, the difference is taken as insignificant, i.e., due to chance, and the null hypothesis of no difference between sample means stands. In case the calculated value of F happens to be either equal or more than its table value, the difference is considered as significant, which means the samples could not have come from the same universe, and accordingly the conclusion may be drawn. The higher the calculated value of F is above the table value, the more definite and sure one can be about his conclusions. Setting UP analysis of variance table. For the sake of convenience, the information obtained through various steps stated above can be put as under. Table 11.1 Analysis of variance table for one-way ANOVA. There are K samples having in all N items. Pause the video to look at the table. Shortcut method for one-way ANOVA can be performed by following the shortcut method, which is usually used in practice since the same happens to be a very convenient method, particularly when means of the samples and/or mean of the sample means happen to be non-integer values. The various steps involved in the shortcut method are as under. I. Take the total of the values of individual items in all the samples, i.e., work out Xij I is equal to 1, 2, 3. J is equal to 1, 2, 3. And call it as T2, work out the correction factor as under. Correction factor is equal to T2. N. J. 3. Find out the square of all the item values one by one and then take its total. Subtract the correction factor from this total and the result is the sum of squares for total variance. Symbolically, we can write total SS. 4. Obtain the square of each sample total, T2, and divide such square value of each sample by the number of items in the concerning sample and take the total of the result thus obtained. Subtract the correction factor from this total and the result is the sum of squares for variance between the samples. Symbolically, we can write SS between is equal to, where subscript J represents different samples or categories. We The sum of squares within the samples can be found out by subtracting the result of 4 step from the result of 3 step stated above and can be written as under. After doing all this, the table of ANOVA can be set up in the same way as explained earlier. Coding method. Coding method is furtherance of the shortcut method. This is based on an important property of F ratio, that its value does not change if all the n item values are either multiplied or divided by a common figure, or if a common figure is either added or subtracted from each of the given n item values. Through this method, big figures are reduced in magnitude by division or subtraction, and computation work is simplified without any disturbance on the F ratio. This method should be used specially when given figures are big or otherwise inconvenient. Once the given figures are converted with the help of some common figure, then all the steps of the shortcut method stated above can be adopted for obtaining and interpreting F ratio. Two-way ANOVA. Two-way ANOVA technique is used when the data are classified on the basis of two factors. For example, the agricultural output may be classified on the basis of different varieties of seeds and also on the basis of different varieties of fertilizers used. A business firm may have its sales data classified on the basis of different salesmen and also on the basis of sales in different regions. In a factory, the various units of a product produced during a certain period may be classified on the basis of different varieties of machines used and also on the basis of different grades of labor. Such a two-way design may have repeated measurements of each factor or may not have repeated values. The ANOVA technique is little different in case of repeated measurements, where we also compute the interaction variation. We shall now explain the two-way ANOVA technique in the context of both the said designs with the help of examples. A. ANOVA technique in context of two-way design when repeated values are not there. As we do not have repeated values, we cannot directly compute the sum of squares within samples as we had done in the case of one-way ANOVA. Therefore, we have to calculate this residual or error variation by subtraction. Once we have calculated, just on the same lines as we did in the case of one-way ANOVA, the sum of squares for total variance and for variance between varieties of one treatment as also for variance between varieties of the other treatment. The various steps involved are as follows. I. Use the coding device if the same simplifies the task. 2. Take the total of the values of individual items or their coded values as the case may be in all the samples and call it T3. Work out the correction factor as under. Correction factor is equal to T2. N4. Find out the square of all the item values or their coded values as the case may be, one by one, and then take its total. Subtract the correction factor from this total to obtain the sum of squares of deviations for total variance. Symbolically, we can write it as sum of squares of deviations for total variance or total SS equals to. We take the total of different columns and then obtain the square of each column total and divide such squared values of each column by the number of items in the concerning column and take the total of the result thus obtained. Finally, subtract the correction factor from this total to obtain the sum of squares of deviations for variance between columns or SS between columns. 6. Take the total of different rows and then obtain the square of each row total and divide such squared values of each row by the number of items in the corresponding row and take the total of the result thus obtained. Finally, Subtract the correction factor from this total to obtain the sum of squares of deviations for variance between rows or SS between rows. 7. Sum of squares of deviations for residual or error variance can be worked out by subtracting the result of the sum of V(th) and 6(th) steps from the result of 4(th) step stated above. In other words, total SS between columns plus SS between rows is equal to SS for residual or error variance. 8 degrees of freedom df can be worked out as under df for total variance is equal to C. R1 df for variance between columns is equal to C1 df for variance between rows is equal to R1 df for residual variance is equal to C1 R1, where C is equal to number of columns, R is equal to number of rows. 9. ANOVA table can be set up in the usual fashion as shown below. Table 11.3 Analysis of Variance Table for Two-Way ANOVA. Pause the video to look at the table. In the table, C is equal to number of columns, R is equal to number of rows, SS residual is equal to total SS between columns plus SS between rows. Thus, MS residual or the residual variance provides the basis for the F ratios concerning variation between columns treatment and between rows treatment. MS residual is always due to the fluctuations of sampling and hence serves as the basis for the significance test. Both the F ratios are compared with their corresponding table values for given degrees of freedom at a specified level of significance as usual, and if it is found that the calculated F ratio concerning variation between columns is equal to or greater than its table value, then the difference among columns means is considered significant. Similarly, the F ratio concerning variation between rows can be interpreted. ANOVA in Latin square design. Latin square design is an experimental design used frequently in agricultural research. In such a design, the treatments are so allocated among the plots that no treatment occurs more than once in any one row or any one column. The ANOVA technique in case of Latin square design remains more or less the same as we have already stated in case of a two-way design, excepting the fact that the variance is splitted into 4 parts as under I. Variance between columns, 2. Variance between rows, 3. Variance between varieties, 4. Residual variance. All these above stated variances are worked out as under Table 11.8. Pause the video to look at the table. Analysis of covariance, ANOVA. Why ANOVA? The object of experimental design in general happens to be to ensure that the results observed may be attributed to the treatment variable and to no other causal circumstances. For instance, the researcher studying on independent variable, X, may wish to control the influence of some uncontrolled variable, sometimes called the covariate or the concomitant variables, Z, which is known to be correlated with the dependent variable, Y. Then he should use the technique of analysis of covariance for a valid evaluation of the outcome of the experiment. In psychology and education, primary interest in the analysis of covariance rests in its use as a procedure for the statistical control of an uncontrolled variable. ANOVA technique. While applying the ANOVA technique, the influence of uncontrolled variable is usually removed by simple linear regression method, and the residual sums of squares are used to provide variance estimates, which in turn are used to make tests of significance. In other words, covariance analysis consists in subtracting from each individual score, that portion of it that is predictable from uncontrolled variable, Zi, and then computing the usual analysis of variance on the resulting y, of course making the due adjustment to the degrees of freedom because of the fact that estimation using regression method required loss of degrees of freedom. Assumptions in ANOVA. The ANOVA technique requires one to assume that there is some sort of relationship between the dependent variable and the uncontrolled variable. We also assume that this form of relationship is the same in the various treatment groups. Other assumptions are I. Various treatment groups are selected at random from the population. 2. The groups are homogeneous in variability. 3. The regression is linear and is same from group to group.